Hey everybody. Today we're going to be talking about rational functions. So the way to motivate this section is of course asking, well, what is a rational function? And a rational function, so in the last section we generalized to polynomials. So in this section we're going to look at simply the quotient of two polynomials. So quotient just means fraction. So the fraction corresponding to two polynomial expressions, as we'll see throughout this section. The main thing to keep in mind is the construction of a rational function. The formal definition looks like p of x over q of x, but again, this is just a formal jargon that simply means a polynomial divided by a polynomial, or in other words, the quotient of two polynomials, as I have written here. So now that we've introduced radical functions, now we're going to go ahead and simplify radical expressions. Now the only difference between a function and an expression is simply the lack of that f of x terminology. So virtually all we have, we're not solving for anything. We're not concluding this problem with an x equals blank. What we're doing instead is simplifying the fractions in each problem as much as we can. So let's start with number one over here. So I notice a lot of people in class, they look at a situation like this and think, well, I'm going to cancel out the 5x in the denominator with the 1 in the numerator. And that's something that you cannot do. You cannot do that in general. Because the 5x is not just dividing that 5x in the numerator, it's dividing both terms. So because it's dividing both terms, if you want the 5x to cancel out with this, then you also need to figure out how it corresponds to this term over here. So it's dividing both terms. So the way I would suggest going about this is treating the numerator as its own expression. And as such, if you can identify any way to rewrite that expression, then we might get a more suitable result that might have some cancellation later on. So in the numerator, so you might notice that there's two terms in the numerator. There's the 5x and the negative 25x squared. They both have a 5x in common. This is just something you will have to see going forward if you notice any of these similarities. So by identifying that the numerator, both terms in the numerator have a 5x in common, we can factor out a 5x. So what's left over now? That's the question. If we factor out a 5x from the first term, which is a 5x, then we just get 1. We still get a term there. It's a 1. It doesn't disappear. And if we factor out a 5x from negative 25x squared, well, when we factor out a 5 from 25, it's division. So negative 25 divided by 5 is negative 5. And x squared, we just factored out an x. So we have an x here. And the denominator still carries. So now we are here at this expression after we factored out the common term in the numerator. And now, because the numerator is, well, technically it's multiplicative, which just means now we have a product of stuff. So notice I just put that dot there. That means we have a product of things, which means if we do have any cancellations, now we can go ahead and do them. So notice the 5x the 5x divided by 5x, we can cancel that. So we can cancel these two, just like that. And so what are we left with? We are now left with 1 minus 5x. And this will be our simplified form. So now we move on to problem 2. And so you might notice, well, still can't cross out anything in its current form. But this problem's different in the sense that the numerator doesn't have any like terms that we can factor out. However, there is something interesting going on with the numerator, and that interesting characteristic is that the numerator is a difference of two squares. So it's a difference of two squares, so we can go ahead and break it down even though there's not any like terms in the numerator or the denominator. So let's go ahead and do that. So remember, x squared minus 16 is the same thing as x plus 4, x minus 4. It's a difference of two squares. So now we can simplify this as x plus 4, x minus 4, divided by 4 plus x, just like that. And again, that's coming strictly from the difference of two squares in the numerator. And it just gives us another way of manipulating the problem to see if we get any helpful cancellations later on. Remember, we're just simplifying here, we're not solving. And so some of you might already notice that x plus 4 and 4 plus x are in fact the same expression. They're just written in a rearranged, different rearrangements. So if you want to, you can go ahead and cancel them now, or you can insert this intermediate step, which I will do now. So the numerator will stay the same. But now the denominator, well, 4 plus x, remember we did this in the last section where we wrote things in standard form. Remember, exponent descending order. So 4 plus x can be written as x plus 4. And so now notice, x plus 4 and x plus 4, since the numerator is now multiplicative, or it's just a multiplication that represents it, we can cancel out the common x plus 4s. Just like that. And guess what we're left with? The x minus 4. And this will be our final answer. Now, simplification doesn't necessarily mean that our final form will get rid of all the fractions. It's just a coincidence that both problems resulted in our denominators virtually disappearing. But in general, simplification is a means to see what the most simplified version of a rational expression or function is without excess information. And so it just so happens, and in the next problem we will notice the same as the previous two, that we'll get a nice simplified form. But that doesn't mean that every rational function simplifies into something like this. So that's something to keep in mind as we go forward. And finally, for problem 3, well, one thing I noticed that I sort of alluded towards in the previous problem was that, well, there is a standard form, because remember, these are, well, rational functions and expressions. They are polynomials divided by polynomials. So as such, polynomials could be written in standard form. So let's go ahead and do that for the denominator, because that is not in standard form. So here, keep in mind that the signs stick with each term. And so we have now we've rewritten the denominator in standard form because it is a polynomial. And now we need to figure out a way to get some commonality between the numerator and the denominator, because they are very close. There's an x and a 4, an x and a 4, and the main observation to make, they are off by a negative sign. So what I'm going to do in the denominator, I'm going to factor out a -1. I'm going to factor out a negative sign. or -1. The way that looks is exactly as follows. So numerator stays the same. The denominator, I'm factoring out a negative sign or a -1. So how does that change the terms within? Well, -x, we just factored out the negative, now it becomes +x. And +4 now becomes -4. So this is the factor, well, this is us factoring out a -1 from the denominator. And so the reason we did that is, well, notice x minus 4 and x minus 4. And now the denominator is multiplicative. The denominator has this multiplying aspect to it, which means we can cancel out. We're going to cancel out x minus 4 and x minus 4. And notice the only thing left over, and it may look weird at first, the only thing left over here is a negative sign. So remember, anything divided by itself is 1. So x minus 4 divided by x minus 4 is 1 with a negative sign in front, which means our final answer is in fact -1. And this will conclude our answers to this problem. Okay, so now that we've simplified and messed around with rational expressions a little bit, now we're going to generalize to the notion of figuring out the domain of rational functions. And there's going to be quite a few problems on your homework that will ask you to find the domain of rational functions. And so what we need to keep in mind, as I mentioned earlier, rational functions are just polynomials divided by polynomials. So we actually, I think it was page 21, 22, something like that, that had all the criteria for how to find the domain if we're not given a graph. And rational functions falls under the first criteria. And so this criteria is so important that I just ended up writing it again. So in particular, this is something you definitely need to know. So the domain of a rational function, you set the denominator not equal to 0 and solve for x. This is something you definitely need to know. This will be a very helpful note, and I have it written in the notes as well, right above these examples. So now we're going to apply this rule directly towards the next three problems. So the first problem we'll take a look at over here. Well, let's find the domain of, well, what virtually results to a fraction. So what we want to do is from here, simply set the denominator not equal to 0, because this rule tells us to do that. So here's the denominator, let's set it not equal to 0. And now that we have this set not equal to 0, we can go ahead and solve for x. So here we have a factored form associated with 0, which, just like as if we had an equal sign, that means we can break this up into a lot more manageable parts. So in particular, we can go ahead and break this up as each one not equal to 0 individually. So there's each part set not equal to 0, and now we can solve for x in each case. Now all you have to do is solve for x. You get x is not equal to +1, and x is not equal to -1 when you bring the number over. And guess what? That's your answer. That is all you have to do for this problem and these types of problems. So it might come down to factoring or solving for a quadratic or a linear expression in some way, but that's the general idea. So let's go ahead and move over to problem 2 over here. So problem 2, it's the same premise. We're finding the domain of what ultimately results to be a fraction. So from this, what we end up doing is we take the denominator and we set it not equal to 0. So we set this not equal to 0. And from here, we simply solve for x. Now, since there's only one x expression, we don't have to worry about factoring. Instead, we can bring the 7 over and then take the square root as such. So we bring the negative 7 over, and now we can think about the square root of both sides. And you might already notice the problem with this, but let's just pretend like we don't see it for a second. With a square, and we apply a square root, that means plus or minus. And so, yeah, you might have already noticed here, we're taking the square root of a negative number. That's not good. We cannot take the square root of a negative number, which means we get no answers from this. We get no answers at all. This doesn't give us any information. If you try putting this in your calculator, the calculator will say domain error. So what gives? We tried to figure out the domain and we ran into an issue. Well, the way we conclude, and that's okay. In fact, that might be a good thing. That means that there's no domain issues at all, which means the domain will be all real numbers. And in fact, you will have an answer choice that will allow you to conclude that. So the conclusion would be that the domain is all real numbers. So that would be your conclusion. And so finally, we're going to move on to problem 3, or part 3 from this example. And what 3 says is it gives you yet another fraction. And, well, it's the same directions. Determine the domain. So we will once again consider setting the denominator not equal to 0 and solving for x. So now we will solve for x. And so you might notice this will constitute a factoring problem, which means we will need to factor this accordingly, which means we need to use, well, guess and check, slide and divide, AC method, whichever method you prefer. What I'm going to use is slide and divide to be consistent with what we've talked about throughout class. So remember, slide and divide. In fact, I'll do this in a different color. Remember, it means we slide the front number over to the last number. And if you're comfortable with this method, you can just skip ahead in the video. You slide the 2 to the -3, and then you can factor this expression. Just like this. So -6 times 1 is -6, and the sum is -5, so it works out. And so remember, don't jump the gun quite yet, because you have to divide by the quantity that you multiplied by earlier. So remember, it's applied exactly like this. We'll go ahead and bring that up here. Because, well, 6 divided by 2, that one's 3, so we can go ahead and do that quickly. But remember, if there's any stubborn denominators, any denominators that cannot be simplified out, then those numbers will come to the front of the factor. Or if you analyze it, if you can foreshadow that negative 1/2 will be one of your zeros, then that's fine. So now we get here, which means this is our factored form of the original expression. In fact, I should put not equals here. And so we solve for x by splitting this up, and we're done. So now x minus 3 gives its own 0. Technically not equal to 0, that sign's important. And 2x plus 1, same idea. We solve for x in both situations, and we're done. And I'll just go ahead and write down both of them, and this will conclude our answer for this problem. We move on from the discussion of domains of rational functions to asymptotes regarding rational functions. And there actually is a correlation between the two, as we will notice in this problem. One thing to keep in mind, though, is, well, when I say an asymptote, and we've talked about asymptotes very briefly before, but asymptotes, as far as we're at now, just think of them as those dotted lines on the graph, as you will notice on the graph provided in example 3 of the notes. And I also wrote out a diagram here for reference. So those are asymptotes, and the graph just gets really, really close to these asymptotes, very, very close. And in fact, for rational functions, for the horizontal asymptotes, you might find that a rational function may touch or cross the asymptote accordingly. It sometimes does happen. In fact, there's a homework question that asks if a rational function can cross the horizontal asymptote, and the answer is yes. Vertical, no, cannot. So with that being said, we are going to look at example 3 from the notes and discuss a few different characteristics about the graph. So the first thing we're going to do is find the domain given the graph. And so remember, since we are given a graph, we look at it left to right. So if we look at this to the left, you will notice that we go to negative infinity. But one thing to keep in mind is that there is only one x value. When we go left to right, there's only one, what's called a discontinuity, something that breaks up everything. So notice we're coming from the left, we're trying to go to the right, and all of a sudden we start to curve up because there's this asymptote in the way. There's something that's preventing us from going to the right to connect with this graph over here. It's this asymptote. So this asymptote in particular tells us a value of x that we are not allowed to have. In particular, this x value corresponds to, well, it's more visible on the graph in the notes, but this is at the point -2. This is -2 right here. And so that tells us at least one value that x cannot be. X cannot equal -2. because there is an asymptote there that prevents us from going from the left to the right in a continuous fashion. But then notice, if we were to hop around that one discontinuity and pick up where we left off, it continues to go on just fine. So it seems like everywhere from left to right, the graph is okay, except in this one spot that breaks up our graph into two different portions. And that is the catalyst that will tell us that for the domain, x cannot equal -2. And that is our conclusion. That's something you will have to start looking for when you're given these graph-based problems. And there's going to be quite a few of them in this homework section. So that's something to keep in mind. As for the range, well, the range is furthest down to furthest up. So it's the same idea. We start to come up, but then we start to level off. We cannot go up forever. There is some barrier in the way. There's some wall in the way. As we keep going up, we hit this asymptote. And this asymptote tells us a value that y cannot equal. In particular, it tells us that y can't equal, and again, the visualization is a little bit more clear on in the notes, but this value right here for which the asymptote is occurring at is +2. It's happening at y is equal to 2. So what we conclude from that is that the range does not allow y to equal 2. And notice I'm saying y instead of x because this is the range. And also they give us a bit of a hint right here. So we keep trying to go up, but we get blocked by this barrier right here. So we skip that because now we know that y cannot equal 2. So let's skip it and start from over here, and notice we can go up just fine without any issues. So what we conclude from that is precisely that y cannot equal +2. This is the thought process you need to have going forward with this. And we'll have another homework question similar to this one if you need a little bit more practice, but this is the idea. And this will help us later on, actually. We'll move on to the x and y intercepts. So those don't change from our previous conceptions before. X and y intercepts, they're just where the graph crosses, well, the x and the y axis respectively. So as we notice on this graph, notice all the blue is representing the function itself. For all the places that intersect the x-axis, well, here's the x-axis. Notice the asymptotes do not count. These are imaginary lines. These asymptotes are only here for our convenience. They are not a part of the graph. So where the dotted line hits the axis, that is not an intercept. That's just an imaginary line that's visualized for our convenience. Instead, there's only one x-intercept, and it's right here, right at the origin, because the x-intercept, or the x-axis, does occur at that position. And so, exactly right here, that's the only place where this x-intercept is intersected by the graph. So as far as x-intercepts go, we only have one, and that is in fact 0. It doesn't want the ordered pair, it just wants the x value. And the y-intercept, same idea. Here's the y-axis. We do not consider the asymptote to be a part of the graph. So where this asymptote hits the y-axis, we do not count that as an intercept. In fact, there's only one place where the y-axis is intersected, and that's again at the origin. And that's okay. You can have the same point being referenced for the x and the y-intercept. It happens. So here the x and the y-intercept end up being the same number, which again is fine. It happens sometimes. And so now we move on to part C, which is finding the horizontal asymptote. Well, if you think about intuition, well, first I mentioned an asymptote's a dotted line. And horizontal, hopefully you remember that's this orientation. So left to right, not up and down. Horizontal is left to right. So it's looking for a dotted line that goes from left to right. And well, look at that, we do have one right here. Here's a horizontal dotted line, a horizontal asymptote. And so what it wants is the equation of that line. Well, it just so happens we did give a description of that horizontal asymptote. We actually gave it right here for the range. And this is where the range and the horizontal asymptote start to slowly connect as two things that are interdependent upon one another. So notice here we put y doesn't equal 2 because asymptotes mean restrictions. But asymptote as a reference is an equation. It just wants this exact expression here, but instead of a not equal sign, it wants an equal to sign. So in particular, what it wants for this answer, so notice it already put the y equals for you. It did that for you. It wrote down the variable and the inequality symbol, or the equality symbol rather. And all you have to do is write the 2. That's it. Or if you want to look back at the graph and convince yourself of that, then the horizontal asymptote is referring to this dotted line, and it just wants to know what y value this dotted line goes through. And that precise y value is 2. Hence why there's a 2 here. So that's 2 different ways you can think about this problem. And so finally, we're going to move on to vertical asymptotes, and I'll mention what an oblique asymptote is in a second. But if anything, vertical is very similar to horizontal, except instead of left to right, vertical's up and down. So it wants a dotted line that's up and down. We just so happen to have one of those right here. So, and also it's prefaced by an x equals. So as I mentioned before, the range and the horizontal asymptote are closely related here. Same idea with the vertical asymptote and the domain. Those are also closely related ideas. And notice for the domain, we got that x was not equal to -2 because we used that to, we found that number by analyzing and going left to right where the discontinuity was happening at. But remember, left to right is the domain. And so that would be one motivation, very similar to the previous part, where we would put, instead of x not equal to -2, this part would take x equals 2. But if you want a different way of looking at it, so vertical asymptote just means the vertical dotted line, still means up and down. It means precisely this right here, and it wants to know what x value this dotted line goes through. If you look closely, it goes through -2. I put 2. Sorry about that. That should be a -2. So, yeah, that one's 2, that one's -2. So, from there, we move on to this thing called an oblique asymptote. It sounds a little bit vague, which that's fair. So what does an oblique asymptote mean? And it turns out in this problem there's not one. An oblique asymptote, so asymptote is still dotted line. Oblique means slanted line. So it's looking for a slanted dotted line. Slanted dotted line. We do not have any slanted dotted lines. We just have them either straight across this way or straight across up and down. You might look on the next example that we have, and that will show a diagonal or slanted line. So we'll see an example of an oblique asymptote. But in this case, I have it set up as y equals just in case, but it turns out we don't have one. So there is an option that allows you to say there's no oblique asymptotes. And that would conclude this problem. So we'll do a problem that's similar to the previous problem. Has a little bit more complexity in it, primarily because now we have, well, not a horizontal dotted line, but we have the aforementioned slanted or oblique asymptote in this problem. And we'll see how to figure that out momentarily. So we'll start off with finding the domain. And so if we're given the graph, remember the domain is left to right. So we try to go left, and we keep going to the right. Yeah, we come from the left, we go to the right just fine, and eventually notice that there is a barrier right here. This barrier that prevents us from going to the right forever. So what this graph would do, it would just get closer and closer to this red dotted line forever and ever, but never cross it. Remember, rational functions, they do not cross vertical asymptotes. So that tells us that for x cannot equal whatever this dotted line is referencing here. And it might seem, well, in this graph, okay, I changed my mind. So they do give you where the dotted line goes through. It goes through x is 0. They don't even put an axis here. They don't put a y-axis, because the y-axis is also where the asymptote is occurring at. So if anything, that tells us that x cannot equal 0. So if we skip that minor snafu and we pick up over here where we left off, then notice going from the left to the right, it goes just fine. It goes smoothly and continuously without any discontinuities, any breaks. So what we conclude from that is that x cannot equal 0, and that comes strictly from the asymptotic behavior right here. That's why. And everything else is okay. It goes from the left to the right just fine with one barrier in the way. Now, if we look at the range, remember the range is up or below to above or down to top. And so from here, what we do is we start from the bottom and we keep going up and see how far we can go until we might potentially hit any asymptotes. But we go up and notice the whole time we don't hit any barriers. There's this diagonal barrier, but it doesn't act as a strict delimiter for the amount we can go up. Same idea down here. This diagonal line does not prohibit this graph from going down infinitely. So we can go up infinitely and we can go down infinitely. And the slanted line cannot modify that in any way. So it turns out that the range is all real numbers. So I have it set up like this, but you do have an answer choice that allows you to put all real numbers. So that would be the answer here. It's all real numbers for the range. Next, we move on to the x-intercepts. So remember, this is where the graph intersects the x-axis. So here's the x-axis right here. And remember, the asymptotes do not count as intercepts. Instead, it's the points right here. It's everything in blue that represents the x-axis. And there's two spots where that happens, here and here. And this problem, it doesn't want the ordered pairs, it wants the x values. These are the x-intercepts. So it wants -5 and +5, and that's it. It wants -5 and +5. We now move on to the y-intercept. So wherever the graph crosses the y-axis, but something you might notice, the y-axis has an asymptote on it, which means there's no way the graph could intersect a vertical asymptote. So what we conclude here is that the y-intercepts, there's none, because on the y-axis there is an asymptote, a vertical asymptote. Rational functions cannot intersect at all a vertical asymptote. So now we look for horizontal asymptotes. The only problem is there are not any horizontal asymptotes. If we look at the graph, are there any dotted lines that go from left to right? The answer is no. There's no dotted lines that go from left to right. So, with that being said, there are no horizontal asymptotes. There's none. There's no horizontal asymptotes. Vertical asymptotes, that's a different story, because we do have one vertical asymptote. We have one dotted line that goes up and down. In particular, it's right here. So now we need to figure out how to express that. So one way you can look at it, the vertical asymptote and the domain are very much related in this regard. And so in particular, the domain says that x cannot equal 0. So the vertical asymptote says, well, give me that answer, but instead of not equal, have an equal sign. And so we supply the answer as the same number. Or if you want to look at it from a different context, vertical asymptote means a dotted line that goes up and down. There's such a line right here. It wants to know the x value for which this dotted line goes through, and that x value is in fact 0. So that's two different ways you can think about it. But now there's this issue with the oblique asymptote, and this wants us to characterize the slanted dotted line over here. So that's what oblique represents, a slanted dotted line. And we do have one. And notice there's a point that they give us, this point of 2 comma negative 6. So we haven't even touched that yet. So apparently that's going to come into play in some regard, as you would imagine. So it turns out that that diagonal line, well, notice I said a line. It's a line, which we can represent lines as mx plus b. So if you can look at that diagonal line and figure out the slope and the y-intercept, then you're done. Something to note about this diagonal line is that it crosses through the origin. Crosses right here, through the origin. That's one of the places where this diagonal line crosses through. And in fact, that's where it crosses the y-axis. And so, with that being said, the y-intercept of the oblique asymptote is 0. So, the y-intercept of the oblique asymptote y-intercept is 0. And now all we have to do is figure out the slope. So this is where the 2 comma negative 6 comes into play. So the slope, we know that the diagonal oblique asymptote here goes through 2 points. It goes through the origin, which is 0, 0, and it goes through 2 comma negative 6. That means that we can characterize the slope as y2 minus y1 over x2 minus x1. And so if you pick either to be y2, y1, I will choose it in this orientation. Negative 6 minus 0 divided by 2 minus 0. And what we end up getting from this is negative 3. And so that tells us the slope, we get the y-intercept, and we can conclude that the oblique asymptote is negative 3x, just like that. And that would conclude this problem. Now that we've talked about how to find asymptotes given a graph, we're now going to move on to finding asymptotes algebraically. So, in a situation where a graph is not provided, how can we figure out horizontal and vertical asymptotes? We have talked about oblique asymptotes, but fortunate for us, we're not going to be looking for determining oblique asymptotes algebraically, so I'm going to just focus on the two, horizontal and vertical asymptotes. We'll start off with the easier one, vertical asymptotes. And vertical asymptotes, I provided a rule here, it's also in your notes, but the rule is for vertical asymptotes, you set the denominator equal to 0 and you solve for x. Now this should sound very familiar. The domain of rational functions is setting the denominator not equal to 0. But asymptotes look at it from the other perspective. They just simply want you to change the sign. That's it. So the domain and the vertical asymptotes are very much closely related. And this is why. It's the same methodology, but it's just a different way of symbolizing it. And I wrote an example here. This example is not in your notes, but it does express an example of this situation of finding a vertical asymptote. So if we have a function 3x divided by x minus 7, notice we're setting the denominator equal to 0, and by solving for x, we just get that x is 7. And guess what? That is the vertical asymptote in this problem. What we're now going to look at are horizontal asymptotes. And as I mentioned a second ago, these tend to be a little bit more complicated asymptotes, only because there's criteria. In fact, there's 3 situations that can happen in finding horizontal asymptotes. And these situations all result from the degree of the numerator and the degree of the denominator, how they compare. And we're going to go through each one of those one by one, as well as look at an example of each situation. So one of the situations is if the degree of the numerator is less than the degree of the denominator. So if the numerator degree is less than the degree of the denominator, then the horizontal asymptote is y is equal to 0. That's it. It's nothing else, it's nothing more, it's nothing less. You just get that one for free. An example of that, the horizontal asymptote of this function is y equals 0. So we need to look at this function and consider to ourselves, well, what's the degree of the numerator? What's the degree of the denominator? And the degree, remember, the degree represents the largest exponent. The largest exponent in the numerator is understood to be 1. So the degree of the numerator is 1, and the degree of the denominator, it's 2. So that's why it falls under the first condition. That's why the degree of the numerator is smaller than the degree of the denominator, as this rule states. A second situation that we have with determining the horizontal asymptote is, well, what happens if the degree of the numerator is equal to the degree of the denominator? And if that's the situation, then the horizontal asymptote is, so it's something we have to sort of figure out. It's y is equal to the ratio of the leading coefficients. So ratio is just a fraction. So it's the fraction of the leading coefficients. And I have an example down here. Remember, these examples that I'm discussing are not in the notes. They're just supplementative. But here, the horizontal asymptote of, so notice, there's this very long rational function here. And notice the only thing that comes out of all of this is y is equal to 15 over 3. And we'll look at that before we simplify it. So where does the 15 and where does the 3 come from? Well, first we have to compare the degrees, as we did for the previous part. So the degree of the numerator here is 8. So the degree of the numerator is 8, and the degree of the denominator is also 8. So that's why this falls under this category of degree equality. And since the degrees are the same, then that means the horizontal asymptote is the ratio, or the fraction, of the leading coefficients. So what's the leading coefficient in the numerator? It's 15. Well, hey, look at that, 15 pops up over here. That's not a coincidence. That's the reason why 15 is over there. And the leading coefficient in the denominator is 3. Well, again, look at that, 3's in the denominator over here. Again, that's not a coincidence. So remember, this is y is equal to 15 over 3. And it just so happens 15 over 3 simplifies simply to just 5. So that's why I have 5 here. So y equals 5 would be our horizontal asymptote for that problem. Finally, our third situation is, well, if the inequality from the first example is flipped. So what about if the degree of the numerator is in fact larger than the degree of the denominator? Then over here we see that the horizontal asymptote simply doesn't exist. And one example of that, if we look at this rational function right here, well, this one falls under that category. So notice I put D and E, it just means does not exist. So let's look at the degree of the numerator and the denominator. So the degree of the numerator, remember, again, the degree is the highest exponent, which seems to be 4. So the degree of the numerator is 4. The degree of the denominator is simply 2. And because of that comparison, since the numerator degree is larger than the denominator degree, it simply falls under this situation. It simply does not exist. Finally, we're going to move on to a few homework questions that are fairly similar to ones we did earlier, but here we're given a function, a rational function, and we're going to not only determine the domain, the range, and the asymptotes about it, but also be able to pick the correct graph corresponding to it. So let's go ahead and look at part A, and notice it says the word shift, which does imply a transformation. So as you can see, transformations are still a theme that we're going to keep seeing throughout the remainder of this class. And so if we think about how the shifting occurs, notice it does say 7 units, and there is a -7 here. You do need to know how that corresponds to the graph. So 1 over x is the parent function. If you look back at our library of functions, 1 over x is one of the functions. It's called the reciprocal function. And so what -7 does here, remember, what it means for shifting purposes is that -7 is going to shift the function down 7 units, because that's what happens when you add or subtract a number to the whole function. So here we're subtracting 7 from the whole function. If it helps, you can think about this precisely as this format. And as such, we can go ahead and conclude that this will be shifted down 7 units. And since it's shifted down 7 units, so what's going to happen, one thing you might notice from the parent function of 1 over x is that it has a horizontal and a vertical asymptote. And so that's something we're going to demonstrate on the graph, because we're going to graph this, but notice it's going to have you graph, or rather it's going to have you pick out of a multiple choice which graph is the correct graph that resembles the function. What we're going to do in the notes is construct the function and describe all the same motivation behind why this graph is chosen the way it is. So what exactly is being shifted down 7? So what's being shifted down 7 is the horizontal asymptote. The parent function of 1 over x does have a horizontal asymptote, and that's being shifted down 7. In other words, the center of activity of the parent function is being shifted down 7. So if we count 2, 4, 6, these do go by 2s, so we would have a 7 right about here. And even on the multiple choice, they will have the dotted line for you to represent the horizontal asymptote. Now this does nothing to the vertical asymptote, which does still exist, but we did not shift to the left or right any, which means the vertical asymptote is actually directly on the y-axis. So we have a horizontal asymptote that got shifted down 7, and a vertical asymptote that did not get shifted to the left or right at all. So now, the graph of 1 over x, we can now apply that now that we have all the shifting figured out. And so what that will look like, there's one component over here where both sides become really close to the asymptotes, and there's also a component over here. So this is what the graph will look like. Mainly the most important thing to identify here is the location of the asymptotes. That's what distinguishes the graphs from one another. So after we have that, now we can move on to determining the domain, the range, and all the asymptotes, now that we're given the graph. So the domain, since we're given a graph, it's furthest to the left versus furthest to the right. So let's see how that goes. Coming from the left, we notice that the graph goes just fine until, once again, similar to the previous problems, we hit a bit of a snafu. The graph does not go to the right forever. In fact, it's stopped by this vertical barrier right here. So that vertical barrier tells us that there's an x value that we cannot attain. That x value in particular is x equals 0. That is where the asymptote is happening at. So if anything, we see that x cannot equal 0. And so you might notice for the domain problem in my notes, I have two parts. And the reason I have two parts is that the inequality symbol will go here and the expression will follow. And so there's a reason I did that, and it will make more sense in the next problem. But here we have that x is not equal to 0. Just simple as that. Because if we notice, x cannot equal 0 because it restricts us from going from left to right continuously. So if we skip around that asymptote and go right back up here, left to right is just a matter of, well, can we do that without any other issues? And the answer is yes, we can. So the only restriction of x is x cannot equal 0. Now we move on to the range. So for the range, that's how far down versus how far up. So if we try to go up from the lowest point, we once again hit a barrier right here. That barrier restricts a certain y value because the range cares about y's. So what y value does that barrier represent? That y value is -7, which makes sense because we shifted down 7. So once again, this tells us that there's a y value that we strictly cannot equal. It's 7. And if we skip around that asymptote, so if we skip around this asymptote and find the graph, we once again try to go from the lowest point here, going up to see if there's any other barriers in the way. And as we see, there are not. So we conclude that the range, well, it's y cannot equal to 7. Now what we're going to do is determine the asymptotes. Now if anything, the oblique asymptote, that refers to a slanted dotted line. There are no slanted dotted lines here. So for the oblique asymptote, there's simply none. There's no oblique asymptotes. But there definitely are vertical and horizontal asymptotes. Remember, vertical is up and down. And we do have an up and down dotted asymptote. And finally, what we have to do, as the problem in the notes suggest, we have to express that as an equation, which means we need to put an equal sign. They will not have an equal sign for us, at least as far as the notes go. So this vertical dotted line, that tells us, well, if anything, this refers to x, and this will in particular be x cannot equal to 0, which makes sense because the vertical asymptote and the domain are very much closely related. They're very much closely related. But remember, for the vertical asymptote, we use the equal sign. We use equality for the asymptotes, not a not equal sign like for the domain. Domain and the asymptote look at the same problem from two different perspectives. So that's why it's important to distinguish between the two. And the horizontal asymptote, well, horizontal dotted line, which is precisely this one. And it wants us to characterize as an equation the representation of this horizontal dotted line. So in particular, the horizontal asymptote and the range are very much related. So if anything, the equation will start off as y is equal to, and it's just a matter of seeing where does the dotted line go through. And we notice that it goes through -7, which again makes sense because we went down 7. So this is -7. And that would be our answer for the horizontal asymptote. Again, the horizontal asymptote and the range, they're very much connected. But notice one says not equal to 7, and the other one does have an equality to, well, -7. I just realized that should be a -7. So if you noticed that earlier, sorry. So we already figured out the oblique asymptote, so that would be our answer to this problem. And we're going to move on to one more problem. Now, what you may notice is, so for this cluster of problems, you're going to notice that a lot of them will resemble the previous example, example 5. But there is one problem on there, and in fact it's this problem, or probably a problem very similar. And it requires one intermediate step before you may continue. And the reason why I isolate this one is because, well, these problems are circulated around choosing a graph based off of transformations. And with this problem, we don't really know what the transformations are. It says, notice in part A, it will say, reflect the graph about some axis and then shift 2 units. So maybe the reflection part might be easier to determine. We'll get to that in a bit. But where does 2 units come from? I don't see 2 anywhere up here. And they do give you 2 as part of your answer choice. So what we need to do, well, when I see a quadratic and I don't know what to do, well, I know that quadratics factor. So let's go ahead and factor that quadratic in the denominator and see what happens. So this one seems to be a fairly straightforward factorization. I see x minus 2 and x minus 2. So let's go ahead and make that substitution. X minus 2 times x minus 2. -2 times -2 is +4, and their sum is -4. So that is the correct factorization. And even furthermore, there's 2 of them. So notice there's an x minus 2 and another x minus 2. So one more thing I would like to throw in is combining them with a square. And the only reason I did that is now we see what the transformation is. Now we see where the 2 is coming from, the aforementioned 2 from the problem. And with that revision, so the other problems will already be aligned in this format. It was just this one problem that I wanted to talk about. And from here, we can go ahead and fill in the blanks. So we start off, it reflects about some axis. And the reason that they're even suggesting a reflection is because notice there is a negative in the very front of the function. So with a negative in the front of the function, see when the whole function's negative, we reflect about the x-axis. So if anything, this is a reflection about the x-axis when the whole function is negative. And then we shift 2 units to the blank, and they're in reference, they are referencing the 2 right here. So remember, when we have a number that's affecting the x directly, what that tells us is that we go left or right. So now we need to figure out whether this is to the left or to the right 2. Well, remember, if we're going left or right, that means the opposite of the sign. So x minus 2, remember, it's the opposite, which means we go to the right 2. And that's how we would conclude this part of this problem right here. We would go to the right 2, because it is the opposite direction from the sign. And that's what that revision helps us determine, at least for part A. And then that helps us determine the correct graph. Now we know that there is a reflection, and we know that the graph shifts 2 units to the right, but the parent function here may not be clear. And in fact, it's not going to be clear because we never talked about this parent function. Now, thankfully for all of you doing the homework, it's going to be multiple choice. So if anything, they will show you what the shape is. And it's just a matter of determining where that shape will shift at. Well, it turns out that the parent function of this is 1 over x squared. That is the parent function. And again, that's not a parent function we've looked at. It is something that they will give you though in the multiple choice part. So if anything, let's go ahead and think about, well, the asymptotes of this. The asymptotes will still be the same as if it were 1 over x. So 1 over x is a parent function you do need to know. That's the reciprocal function. And it by default has a horizontal asymptote on the x-axis and a vertical asymptote on the y-axis. So now we need to determine, how do those asymptotes shift? Well, reflection about the x-axis will not change any asymptote. So a reflection about the x-axis, if we have a vertical asymptote, the reflection will return the same asymptote. So that doesn't affect anything. I'll show you how it affects things later. Mainly it's the shifting that will affect the asymptotes. And if we shift to the right 2 units, well, a horizontal asymptote, if you shift it to the right 2 units, it doesn't change anything. But a vertical asymptote, if you shift it to the right 2 units, that will change. That vertical asymptote will go from x is equal to 0 to now x is equal to 2. So if anything, we can now construct that asymptote at 2 because we shift to the right 2. So now that asymptote will be shifted right here. But the horizontal asymptote never got shifted. The horizontal asymptote only gets affected when we go up or down. So that will continue to stay on the x-axis. On the x-axis. It might be hard to see, but the multiple choice will have this part for you. And now it's just a matter of drawing in the shape. And again, you don't have to know what the shape is offhand. We haven't talked about it yet, but I will tell you what the shape looks like. It's very similar to 1 over x. So 1 over x and 1 over x squared, they both have this characteristic in common. They both have that characteristic in common. However, since it's an x squared, that means that everything is happening above the asymptote. So that means we will have this occurring instead of, say, this happening down in this quadrant or this region. And if you want, you can compare the shape of this to the shape of the previous problem, and that would give you a nice distinction. But nonetheless, notice that the center of information shifts over twice, and so that would be the correct graph. That would be the way of determining the graph of the function. And now, with that, we move on to the domain, the range, and all the asymptotes. So if anything, the domain will, no matter what, still left to right, because we do have a graph available, and we start from the left, we see how far to the right we can go. And notice, we start to hit a barrier. And that barrier, so this is the domain, so that this barrier tells us something that x cannot equal. It's x because of the domain. So what's that x value in particular? Well, let's see, where does the asymptote hit the x-axis? Hits it right at 2. And it does make sense that it's 2 because these go by increments of 2. So if anything, that tells us that x cannot equal 2. And so if we skip around that detail and continue to go from left to right with this side now, everything goes very smoothly without any more breaks. So that tells us that x is not equal to, so that'll be the first blank, and then positive 2. And so we move on to the range. Now notice the range is going to be a little bit different in this problem. That's another reason that makes this problem a little bit more complex. The range, so notice there's nothing going on down here below the horizontal asymptote, which means we're not coming from negative infinity. So we are not coming from negative infinity, which means we need to figure out the lowest point of the graph. Remember, the graph is in blue. The lowest point of the graph seems to be, well, if we follow either end, it seems like we hit a barrier that prevents us from going down infinitely, and that's what we need to identify, what the barrier is. The graph seems to be larger than this barrier. Remember, this is the range, so this is y. But it seems like everything is greater than, so if anything, I just used the key word there, everything is greater than this horizontal asymptote. We're not going to use a not equal for the range. For y, we're going to use greater than. So we're using greater than because everything is strictly above a certain barrier. This is different than the previous problem because there was stuff alternating between the asymptotes. Here everything is in tandem to one side of the asymptote. So the lowest we can go is 0, exclusive, because of the barrier, and everything above that, we can go up just fine without issue. So this is happening at y is equal, or well, this is happening at 0, and so we have y greater than 0. So this one's definitely a kind of challenging part. You can definitely pause this and try to figure that out. And there is another problem similar to this idea, so that is something you will need to know going forward. So let's go ahead and move on to the asymptotes. Now, the vertical asymptote is very similar to the domain. They are very closely related. And the vertical asymptote here, well, we can look over here. Vertical is up and down. So it wants to know the vertical asymptote of the up and down dotted line. That seems to be happening at x is equal to 2. And as you will notice in the notes, they do want an equation. So this is, in fact, x is equal to 2 for the vertical asymptote. Horizontal asymptote. So horizontal asymptote and the range are very closely related. The horizontal asymptote wants to know the equation of the barrier. So the barrier that goes in the horizontal orientation is right here. And so horizontal asymptotes are normally prefaced by y equals. Again, that's by default. So horizontal asymptotes are related to the range. So that means by default, their equations are y equals, just like the range is, it's corresponding to y's. And so that y value seems to be, well, 0. So this is y is equal to 0. And then oblique asymptote, that is any slanted dotted lines, but we do not have any slanted dotted lines, so you can definitely put none here. And that would conclude this problem.